Hello everyone, I am Bharat Singla and welcome to Learn Competitive Programming with CodeChef. If you desperately want to master competitive programming and get your hands dirty in data structures and algorithms, then this is a one-stop destination for you. Every week, we upload problem explanation from CodeChef's contests, conceptual videos on various programming paradigms, and also conduct live interactive sessions. But before we start off, here's a reminder for you to hit the subscribe button if you haven't yet already. Great. Now that you have subscribed, let's get started. So in this video, we'll discuss a medium level problem, Hail XOR from CodeChef's December challenge. There's only one prerequisite, that is the basic XOR operator, like the very elementary XOR operator. You should just know how it manipulates the bits. Although I'll still briefly cover this in the course of the explanation. But before we begin, do you guys know that CodeChef also conducts free live sessions on Unacademy where we try to teach every possible topic related to competitive programming? We have list of courses for all skill levels, like beginner courses such as Introduction to Programming in C++ and Java, intermediate courses like a course on number theory, recursion, basic data structures, as well as advanced courses like dynamic programming, graph theory, segment trees, and many more. Here, you will be taught by top coding experts who are IUI medalists, ICPC World finalists, and have worked at companies like Google, Flipkart, LinkedIn, and basically all those tech giants. All you have to do is register yourself at Unacademy by clicking this button Start Learning here and choosing your goal as competitive programming. But this isn't just it, guys. You can also go for the Plus subscription where you get additional benefits like individual support and full-time doubt solving. You also get the access to the problem sets curated by these coding experts for each topic. And to add the icing to the cake, there are mentors who are going to resolve all your queries, and they are 6-star and 7-star coders as well. So subscribe to Unacademy Plus, guys. Don't miss this golden opportunity of learning from the best in the world and kickstart your programming journey today. You can use the code Bharat27 to get an instant 10% discount as well. So hurry up, guys, subscribe to Unacademy Plus. So let us start off with the problem statement. So it is saying that given a sequence A, so you'll be given a sequence A of length n, you need to perform this operation, the given operation, exactly x times. Fine. So the operation, let me just brief you what it says. It says to choose any two elements from the array AI and AJ and also choose one non-negative integer P and XOR both of them. So basically replace AI with AI XOR 2 to the power P and replace AJ again with that same number 2 to the power P. Fine, where this is the XOR operator. So in other words, you can say that choose any two elements from the array and XOR both of them and replace them with any power of 2. Fine. So this is the operation given. And let's say I have taken this example here. So if we are given this array 3, 4, 6, 7 and I equal to 1, j equal to 3 and I have chosen p equal to 2. So basically the power of 2 that I am taking is 4. So first I'll XOR 3 with 4 and 3 XOR 4. So 3 XOR 4 we all know is equal to 7, right? This can be easily calculated and j equal to 3. So replace this element as well with 6 XOR 4. Now what is 6 XOR 4? It is nothing but 2. So replace this with 2 as well. Fine. So this was one operation and we need to perform this operation x times. Fine. And we need to find the lexicographically smallest sequence which can be obtained by performing this operation x times. Fine. So now what is the lexicographic ordering? So it is exactly same as the dictionary ordering. So you can say that, okay, so here I have two words S1 and S2. Let's say A, B, C, D, E and A, B, C, E, E. So how do you say that this word or this word will come before the other in the dictionary? You say this by taking every corresponding letters, right? So first we'll take this A and this A. So they are equal. So we'll move on to the next character, that is this. So this B with this B and then go to C, then go to D. And here D and E, they are not equal and D is smaller than E. So irrespective of the letters on the right, we say that S1 is smaller than S2. Fine. And it will come before S2 in the dictionary. Same goes for sequences as well. We can say that given these two sequences, we go to every corresponding element, right? So 1, 1, then 2, 3. And here we know that 3 is greater than 2. So we can very confidently and safely say that S2 is greater than S1. Fine. Irrespective of what the elements on the right are. Like in this case, all of them are 0, very small. And here we are given 3 and 4. But still, we are not taking into care the elements on the right. So since 2 is smaller than 3, we say that S1 is smaller than S2. Now this is the lexicographic ordering, exactly same as the dictionary ordering. And we need to basically perform this given operation x times optimally so that we end up with the lexicographically smallest sequence which can be obtained. So now that we are comfortable with the problem statement, let us move on to the approach required to solve the question. And basically, we are going to cover everything like the observations, the intuition, and all the steps, and we'll just essentially try to solve the problem. So let us move on to the approach. Now, all those who don't know about the XOR operator, you can refer to this chart. The first point to note is that we all know how XOR operator works, right? But let us think about something that is very special with XORing a number n with a power of 2, right? So what is so special about XORing any number n with a power of 2, right? Not just any number, but a power of 2. So first thing to observe is that if we write any power of 2 in base 2, right? So in binary form, how does it look like? So let's say I take 8. So this in binary form is nothing but 1000, right? In if we take 16, it is 10000, right? For 4 as well, it is nothing but 100, right? So what we can conclude is that any power of 2 when written in binary form has nothing but a single 1 followed by a lot of zeros, right? And that will depend on what key we take. Fine. So this is how a binary form of any power of 2 looks like. And how does it apply here? Let's have a look at that as well. So if I take n is equal to 42, any arbitrary number. So what is this in binary form? It is 101010, right? 1, 2, 5, 10, 21, 42. Fine. So this is its binary form. And what happens when we XOR it with a power of 2, let's say 8. So XORing it with 8, that is 1000. So what is the result? So first to match their lengths, let me just prepend some zeros. So now 0 XOR 0 is 0, then 1 0 is 1, 0 0 is 1, 1 1 is again 0, then 0 0 will again give us 0, and 1 0 is 1, right? So now what can you conclude from this? So after we have XORed, notice that all the bits, so this bit, then this bit, this bit, this bit, all of them remain the same, right? Why? Because all of them have 0 as their corresponding bit. And from this chart, we can clearly see that any number, any bit, basically 1 or 0, XORed with 0. So like here, in both of the cases, it's 0. So 0 XOR 0 is 0 and 0 XOR 1 is 1. So from 0, we are getting the same bit again, right? 0 stays 0 and 1 stays 1. But what happens when we XOR with 1? So it is 1 XOR 0 is 1 and 1 XOR 1 is 0. So what basically we can say is that it is going to toggle the corresponding bit. So 0 becomes 1 and then 1 becomes 0, right? So if we try to apply this here as well, so here since there's 0 everywhere, so all the bits are going to stay the same except for this bit, right? So this bit here. This bit will toggle this bit of 42 and from 1 it is going to bring it to 0. Had there been 0 here, it would have brought it to 1. So second observation, but before moving to that, our final aim, remember our final aim is to get to a lexicographically smallest sequence. So to reach closer to optimal solution, we need to continuously reduce these numbers. Again, taking this above example again. So here from 1 we brought it to 0, right? So are we decreasing the number? So yes, we are decreasing the number. This in decimal form is nothing but 34. So by XORing it, we have come closer to the optimal solution, right? But what if here instead of 1 we were given 0, right? Then this would have become 1, right? And that would have increased the number, right? Because we are changing only one bit at max, and if we are bringing from 0 to 1, so we are increasing the number. So that's why this is not optimal. So again, as a quick exercise, you can pause the video here. I want you to think about all the powers of 2 that are going to help us get closer to the optimal solution. And if you are able to get this, that means you are following very well, right? So you have understood whatever we have discussed till now. So just pause the video and think about all the powers of 2, that is all the 2 to the power p numbers of this form that will decrease the number when XORed. So the answer to the exercise is that one power that we have already discussed is 8. The other one is 2. Why? Because note that we are always decreasing the number when we are matching a 1 with a 1, right? Because that would give us 0 as the XOR. So I could either take a power of 2 where there's 1 here, right? So 1 and 1 would correspond. I could also take a power of 2 where there's 1 here, like in 8, right? And if I take 1 here as well, So 1 0, that is 2. So that will also decrease the number, right? So this was the answer for this exercise. And now this has given us another great observation as well. Now what is the observation? That there were three powers of 2 that helped us decrease the number. But which one helped us decrease the number the most? Yeah, it was not 8. Instead, it was 32. Now why? Fine. So note that if we are changing the MSB of the number, MSB the most significant bit, and as the name suggests, it is the most significant bit. If we are able to toggle that from 1 to 0, we are drastically reducing the number. So what you can do is that given n, let's say 42 again, so it was 1 0 1 0 1 0, right? So which power of 2 you can take? You can, to generalize, you can say that 1 followed by zeros, right? And this one should match to the MSB. And the number of zeros you are taking will depend again on its length, and that will depend on n again. Fine. And to generalize it even more, so the second observation, the conclusion of the second observation is that take the largest power of 2. So largest power of 2 that is smaller than or equal to n. This will help us toggle its MSB. So this was the conclusion of the second observation, right? And now let us make the third observation as well. Now again, we are now just getting a little away from XOR. Now the third observation is based on that we need to find the lexicographically smallest sequence. And in lexicographic ordering, we are just concerned about the initial elements. So first, what we can take away from this is that first, first reduce numbers on the left, only then think about right, right? Then care about right. Until and unless we have reduced the leftmost element of the sequence to as low as possible, we only then should move on to the right elements, right? Because if we are reducing the right elements but the left elements are greater, then it's not the lexicographically smallest sequence, right? First bring it to zero or the lowest possible, and only then XOR the right numbers. Right. So this was the third observation, a little straightforward observation. And the fourth observation, right? There are a lot of observations in this question. And the fourth observation, very similar to the above one, is that now again note that we need two numbers here, right? I and j. So what we have taken away from the above points is that take I to be as less as possible, and take the largest power of 2, right, for I. So for I, take the largest power of 2. And now we want to find the j as well, right? So how do we find that j? Now again, we need to reduce the numbers, right? There's no point increasing a number. So make j traverse from I to n, or I plus 1 to n, right? So make j go from these two elements, right? From I plus 1 to n, and make it traverse, right? And if at any point we are able to find that, okay, we for to decrease I as low as possible, that is our first priority as well, take its largest power, right? That is smaller than I. So this is the number, the power that we had to XOR, we have got this. Now, what's the second element that we should choose, right? So how to figure out the j? Well, that's simple as well. Traverse from I plus 1 till the end, and then if at any point we can say that a of j is becoming smaller by XORing with this largest power of 2, then XOR it, or otherwise again move on to the next element. Fine. So keep on traversing until this largest power of 2 XORed with a of j is smaller than a of j what initially was. Right. So if you are ending up with a smaller number, XOR it, or just move j. Fine. So and if we are unable to find any element that is getting smaller by XORing with this, so and in that case we can simply XOR the last element, because that has the least lexicographic effect on the array. So now here we have almost solved the question, except for one very major issue that we are having, is that we were to perform exactly X operations. So let me just draw an array. So if let's say I was initially given 10, then 9, then 7 and 5, right? So if I am given this array and I am given X equal to 100, right? So now just by seeing how large X is, we can simply say that we are going to get to the optimal state before doing X operations, right? Or if I was given 1000 here, right? So I can guarantee that I can somehow come to the optimal state without even performing X operations. But we have to perform at exactly X operations, right? So now our point is to how to accumulate those remaining operations, or how to somehow adjust those operations so that we affect our optimal state the least, right? So
Again, a quick exercise for you. Taking 0, 0, 0, and 5, that was the last element or something like that, 3, 2, anyone, any number, but zeros and the last element could be any number. So is this the optimal state that we can get? Right? Can we achieve something better than this if we have, let's say, infinite operations, or if we still have operations left? Can we achieve something better than this, where there are zeros followed by any number? So the answer is that no. Now why? Because we need to choose two numbers, two elements from the array in one operation. So even if I take this element so that I can reduce this, I need to take some element right on its left. So I need to take this element or this element, right? But now what if I XOR this with, let's say, 4? So I will reduce this number, right? This will become 1, but this will then become 4, right? And we don't want that, right? This is the optimal state. We don't want to change any numbers on the left just so that we could lower the number on the right. So once we have reached this state, the answer is that we cannot do anything better, right? Because we need to choose two elements, not simply one element. So let's say I somehow brought this to this state, and I still have, let's say, I was given 1000 operations, and I still have, let's say, x equal to 2 operations left. So it took me 998 operations to come to this state, but now still two operations are left. So how do I somehow accumulate them? Now this is the major question. So the first clear observation is that when x is 2 or 4 or 6 or 8, right, when x is even, we can come back to this optimal state. Now how? Now this is another interesting property of XOR, that okay, so if I take A and I XOR it with B, right? And I again XOR the resultant with B. So this is nothing but A again. This is one interesting, very interesting property of XOR, that XORing any number with a number two times or four times brings it back to it what it originally was. Right. So we can again apply this here as well. What we are going to do is I can simply take any two elements, let's say this element, and XOR both of them with 4, 8, or any number. Right. So if I take 2, now these two become 2 again, right? So this is 2 now, this is 2 now, and I can again take these two numbers, right? So take these two numbers, again XOR them with the same number 2, and this will again bring it back to 0, right? So I have again come back to what I originally was, and that we have proved was the optimal state. So this is what you can do when x is even. Now what about x is odd? So if x is 3 this time, so what can we do now? Now the answer is that yes, again I can come back to this original state. Now how? This was a very tricky part. I myself initially thought that if x is odd, then simply XOR the last two elements, because in any case 3 we can reduce to 1, right, by performing this two operations, but there's still one left, right? And in case of 5 also, we can perform 4 operations, but 1 will still be left. So if x is odd, then simply XOR the last two elements. But this is not the correct approach. Why? Because we can do something smarter again as well. So let's say I take these two elements, right? So these two elements, I XOR them with 2. Fine. So this is in binary form, it is 1, 0, 1, right? This is the binary form of 5. And that XORed with 2 will give us 1, 1, 1, that is 7. So this will become 2 and this will become 7, right? Now what I can do is I can take these two numbers, right? So this number and this number, and again XOR it with the same number that I previously XORed. So again taking 2, I XOR this, and this becomes 5 again. Again this property follows. XORing the same number with 2 twice will bring it back to 5, and this will become 2 again. Fine. And now most of you would have observed that now we can take these two numbers and XOR them with 2, and this will again bring it to 0. Fine. So this was very smart trick that we can apply here. When x is odd, we can still come back to its original solution. But again, there's some trick here. Now the point is that we need to have at least three elements, right? Three or more elements to perform this smart trick, right? Because we are taking three elements here, right? So we need to have at least n is equal to 3 or greater than that. Otherwise, we cannot perform this cunning trick, right? So there's another condition that arises, that if x is even, so we can simply have this state again, and if x is odd, we can still come back, but only if x is odd and n is greater than or equal to 3. Right? So this was the other condition. And if the x is 1, so what if x is 1, right? So we have this state, then we cannot do anything. We have to simply XOR the last two elements with 1. That will just like if this was the original state, right? So XORing both of them with 1, this would give us 4, and this would give us 1. So this is the best we can achieve if the remaining operations is 1, right? XORing the last two elements again has the least lexicographic effect. and XORing them with the smallest power of 2 will make 0 only 1. Had we taken the 2 to power p equal to 4, so here it would have become 4, right? But that is not optimal. Take 2 to power p equal to 1 and then XOR the last two elements. So these are the a few conditions that we need to take care. So let's quickly summarize. So the first thing that we saw was how XORing with the power of 2 works. And from this we concluded that only the p plus 1th bit will change, and that will get toggled from 1 to 0 and from 0 to 1, and all the remaining will stay the same. Right. The second thing that we saw was to bring it to a smaller number, we need to match a 1 with a 1. Right. And to drastically reduce the number, we need to toggle its MSB. That way is the most significant bit. So for that, to generalize it mathematically, take the largest power of 2, that is smaller than or equal to n. This is going to toggle its MSB and reduce it drastically. Then the third point we saw was to first reduce the numbers on the left and then take care about the right to get the lexicographically smallest possible array. Fine. And then we saw that the largest power of 2 we take for I, that is one pointer that is going to be on the array that will initially be the 0, the 0th index, right? And we are going to shift I as well as another pointer j. And j is going to traverse from I plus 1 to n. And for every a of j, we are going to XOR it with this largest power of 2, for that was for I. And we are going to check if we are getting a smaller value. If yes, then we are going to XOR and replace that. Otherwise, we are going to shift j. Fine. And if we are unable to find any element that is getting smaller by XORing, so then we are simply going to XOR the last element, even though it's increasing, but that is the best that we can get since it will have the least lexicographic effect. Fine. Then the next thing that we saw was if we have remaining operations, right? Like if we ended up in an optimal state before consuming all the X operations, here we saw that if X is even, we don't need to do anything. And if X is odd and the length is greater than or equal to 3, then again, we don't need to do anything. But if the remaining operations is 1, right? Or if it is odd and N is only 2, then we need to perform one operation, which is to XOR the last two elements with 1. So this was it for the summary. Now let us move on to the implementation, which will be in Python. So first, we are going to import the math library in Python. And why? So just we can define this utilities function, greatest power of 2, that will take a parameter n, and it is going to return 2 to the power int of math of log base 2 n. Fine. So this will, as its name suggests, return the greatest power of 2 smaller than or equal to n. Fine. Then take test cases input and repeat this code test cases times. So first take n and x, the input, as well as the array, and initialize I is equal to 0, right? The first pointer, the one with the higher priority. Then a while true loop, so an infinite loop, and at certain conditions we are going to break out of it. So if x is equal to 0, basically we don't have any remaining operations left. So in that case, simply break out of the loop. We cannot do anything further. And now check while I is less than n minus 1. So while I is in the constraints of the length of the array, and why n minus 1? Because of 0 based indexing, right? And ARR of I equal to 0. So if we have ARR of I is equal to 0, keep on incrementing it until we find a non-zero element. And if I is equal to n minus 1, so we have reached the end. In that case, we have to break because we need another element j, right? So there's no space for that. So I has to be less than n minus 1. Again, n minus 1 because of 0 based indexing. So first, so once we are successful with all of this, we are going to initialize this variable GPO to the greatest power of 2 for the ARR of I, right? And then XOR ARR of I with GPO2, exactly as we saw it in the discussion, right? Then initialize the second pointer J, that will be I plus 1, and again an infinite loop while true loop. So if j is equal to n minus 1, that is we have reached the end and we could not find any element that gave us a smaller value when XORed. So we have no choice but to XOR it with GPO2 and break. And else if ARR of j XORed with GPO2 is less than ARR of j, right? So we are getting a beneficial value. So we are going to XOR and replace it and again break out of the loop. And if we are unable to meet any of the conditions, simply keep on incrementing j. Fine. And remember to decrease x, right? Decrement x because we have consumed one operation, right? So x minus equal to 1 as well. Finally, I'm going to check that if x is equal to 1, right? If the remaining operations are 1, or x is odd and n is equal to 2, right? In that case, we have no choice but to XOR the last two elements with 1. Finally, print the values of the array but again, no square brackets and those commas. So we need this star notation in Python. It looks fine. And now I've already copied the code and pasted it here on the submit tab. Now let's hit the submit button and hope for an easy. But remember, don't just watch me code out the solution. After the video ends, go and try to upsolve the question, that is, code it out yourself, so that it enhances your implementation skills and you gain the confidence that yes, you are able to understand the question. Also, give this video a like if you got an AC and comment down your submission link in the comment section so that we can all appreciate your effort. And yes, we got an AC. This was a correct solution, and this was it for this video and the implementation as well.